Hi friends, let's continue our discussion. Last session we have seen how error can be detected. Now let us try to correct the error. So this is the situation when retransmission is not possible, then we have to find some way to correct if the data we received is erroneous. But yes, definitely it is a tiresome process. It is a very difficult process, but the Hamming code is the one which comes to our aid. And in this, let's assume that we are working with a 4-bit transmission. So 4 data bits are being transmitted. So for transmitting 4 bits, we need 7-bit coding, 7-bit Hamming code, so that 1 bit of error can be identified. So here the parity bits are used. So for 4-bit of data, if you want to identify one erroneous bit, then we need 3 parity bits. It can be either odd parity or even parity as per our protocol. And these parity bits are arranged according to 2 to the power. So first parity bit will be at 2 to the power 0, that is 1. And second parity bit will be at 2 to the power 1, that is at 2. And third parity bit will be at 2 to the power 3, that is 2 to the power 2, that is 4. And next will be at 8, 16, 32, and so on. All other bits can be used for transmitting the data. So out of 7 bits, 3 bits are reserved for the parity, that is the first bit, second bit, and fourth bit, and the other 4 bits, that is the third bit, fifth bit, sixth bit, and seventh bit, are reserved for the data. Okay, that's a protocol, and how it is used is whenever a data is given, say 1011 is to be transmitted, then we have 1 here, 0 here, 1 here, and a 1 here. So this we need to calculate, this we need to calculate, this we need to calculate. So the P1 is related with the least significant bit, and P2 is the next least significant bit, and P3 in this case is the most significant bit. That means P1 is trying to work with this bit 1 0 1 0 1 0 1 and so on. P2 works for the central bit and P3 works for the leftmost bit. So we are looking at P1 is responsible for all the bits which have the LSB equal to 1. That means the sequence, the positions are at 1 we have a 1, at 3 also we have a 1, similarly at 5 and 7 we have a 1. So that means P1 is responsible for identifying error in either 1, 3, 5 or 7. In the same way, P2, that is, it is second bit, it is 1 at 2, then next one is at 3, then we have a 0 here, 1 and 1, that means 6 and 7. Same way MSB, 1, 1, 1, 1, we have at 4, 5, 6, 7. Right. So if you want to find out what is P1, so we need to first define what parity we are using. Say later we assume that we are working with even parity system. Then for P1, what are the bits we need to work with? 1, 3, 5, 7. What is there at 1? We don't know. What is there at 3? We have a 1. What is there at 5? we have another 1. And what is there at 7? At 7 we have a 1. So there are 3 ones, and we want even parity. That means the number of ones here is 3, which is odd. So we, to make it even, we need a 1 here. So if this is 1, then this whole thing, the P1, if P1 is 1, then this whole thing will be an even parity. So use a 1 here. Okay, now for P2. P2 is responsible for identifying the errors in 2, 3, 6 or 7. What is at 2? We still don't know. What is at 3? It is 1. What is at 6? It is 0. What is at 7? It is a 1. So there are 2 ones already. So 2 means it is already even. So if you add a 1 here, then it becomes odd parity. So to ensure that this is even, so we must put a 0 in place of P2. Same way for P3. P3 is for 4, 5, 6, 7. What is there at 4? 4 is still unknown. 5 is 1. 6 is 0. 7 is 1. So there are already 2, which means that the parity is already even. So we need to put a 0 at this place. So that completes the total, the data we need to transmit. So the data we need to transmit is 1 0 1 0 1 0 1. So how that is used after receiving? So this is a first, second, third, fourth, fifth, sixth, seventh. So how it is used is we just use XORs at the receiver. The first parity P1, P2, P3. So P1 talks about 1357. P2 talks about 2367. And P3 is about 4567. So if the correct values are received on the other side, so P1 is 1, P2 is 0, P3 is 1, P4 is 0, P5 is 1, P6 is 0, P7 is 1, so we have at P1, if you look at it, 1, 2, 3, 4, 4 ones are there. So it is even number of ones, therefore the output is 0. If you look at P2, 1 and 2, 2 number of ones are there, which is again even. So when you XOR, you get a 0. And at P3, again you have 2 number of ones. So if you XOR, you get 0. That says P1 is 0, P2 is 0, P3 is 0. All 3 are 0. That says that there is no error. Done. Now assume that 1 bit of this we received wrongly, maybe P3. Instead of 0, we received a 1. So P3, it is 0 here instead of 1. There was another P3, it is 0 here instead of 1. There is no P3 here. Now what would happen is there is 1, 2, 3 number of ones. So when you XOR 1, XOR 1, XOR 1, the result will be a 1. And here we have only 1 times 1 is occurring because this 1 has become a 0. So 0, 0, 0, 1. That means only once there is a 1. So the output of this also becomes 1. I'm sorry. Whereas here we have 2 number of ones which is even. Therefore, it remains 0. Now it says that P1 is raising an alarm, P2 is also raising an alarm, and P1 was responsible for 1, 3, 5, 7, and P2 is working with 2, 3, and 6, 7. 2, 3, 6, 7. So what is common? What is common here? The third bit is common in both of them, and seventh bit is also common. But if seventh bit had changed, then P3 also would have been 1, but P3 is not 1. Therefore, we can conclude that the culprit is the third bit. So what we received is 0, but we should have received a 1. So it should have been 1, 0, 1, 0. We have received a 0, but we should have received a 1. So we can get it, this bit corrected. So that's a logic of error correction. But yes, just for one bit of correction, we are using 3 parities for 4 data bits. So when you are working on a bigger size of data, then the parity bits will be large. So in all, you are going to waste lot of data in parity just for sake of 1 bit. And if you go for 2-bit checking, 3-bit checking and all, then this process grows exponentially and becomes too costly. Hence, it should be avoided unless and until it is essential. Like if you are receiving data from a polar satellite, then the data will be available only once in the revolution. So you can't afford to miss it. So if by mistake something went wrong and you received with error, then make sure to correct it, because there is no chance of retransmission, because you cannot get that polar satellite back onto that position and scan it again and transmit again. So that such situations where the quality of the data and the importance of the data is very high, only then we go for this. If data is available for retransmission, we just avoid this correction. We just be happy with the detection. That's a simpler process. So if we are able to detect error in the data, then we can request back the transmitter to retransmit it. And as long as we don't get it correctly, we can ask it to retransmit. So that is a little easier and is cheaper compared to the efforts we put in correction. So that's something to do with error detection and error correction. Thank you.